Hello, everyone. My name is Zachary Wilkerson, and alongside Pravina Hariharan, we are going to be discussing the research paper Towards an Automatic Turing Test Learning to Evaluate Dialogue Responses. We start off with the concept of moving towards human systems. An important goal in artificial intelligence is to pass the Turing test, a test formulated back in the 1950s to test if a system can create meaningful human discourse. One of the first systems to pass this test was ELIZA, a rule-based system we should all know by now. Systems like these, known as non-task-oriented dialogue systems, look to the Turing test to evaluate performance. Unfortunately, this test is severely limited, as it requires live human interactions, as well as instructions designed specifically for the human user. Another issue with the test is that the quantity of knowledgeable evaluators is limited for specific domains, making it difficult to even perform the test. So the typical solution here would be to measure the quality of system responses instead of the humanness of system responses. This correlates a quote-unquote good chatbot with one whose responses are scored highly for appropriateness. Word overlap metrics, such as BLUE, have been used, although they are known to be biased and correlate poorly with human judgments of response quality. These word overlap metrics fail to capture semantic similarity between a response and its reference response. So, when there are little to no words in common between the response and the reference response, one obtains a low metric even if the generated response is a reasonable human response. We can see how this becomes an issue for dialogue, as the number of appropriate responses is large due to the flexibility of spoken language. Word overlap metrics also fail to consider the context of the dialogue for similar reasons. Take, for example, the conversation shown at the top right of the screen. Speaker A and B set the context of the conversation. Speaker A says, "Hey, what do you want to do tonight?" And speaker B replies, "Why don't we go see a movie?" Now, a model could give a response, "Nah, let's do something active." Whereas the reference response was, "Yeah, the film about Turing looks great." Now, this is a clear example where word overlap scores fail for dialogue evaluation. Although the model response was reasonable, "Let's do something active," it has no words in common with the reference response, "Yeah, the film about Turing looks great," and therefore would be given low scores by word overlap metrics. What this means for us is that we desperately need more effective ways of evaluating dialogue response quality. And it would be even better if we could do this automatically. With that being said, we turn to neural networks. Now, these neural network models are being trained end to end to optimize the likelihood of generating a response from some designed corpus. Such networks have allowed us to improve the responses from dialogue systems far beyond those responses one could generate way back in the 50s. However, neural networks require various iterations with different hyperparameters, all which require output response evaluation. However, obtaining such human evaluations would be far too expensive and time consuming, as we'd have to check every model with every different variation of hyperparameters. So what do we do? In this paper, an automatic dialogue evaluation model, which we refer to as ADAM, is proposed, which trains a hierarchical recurrent neural network, semi-supervised, using a data set of appropriateness scores to various dialogue responses to predict human scores. Now, in order to understand this model, we need to understand what's happening under the hood. We begin with an overview of neural networks. On the left, we see a typical neural network, which we refer to as a multi-layer perceptron. In this network, we send our inputs through hidden layers until it reaches the output layer, where an estimate is made and errors are calculated. These errors are then sent backwards through the network through a process known as backpropagation. And the weights that link all of these layers together are updated based on a proportion of the error that was sent back. One issue we encounter with this approach is that in some cases, the amount by which we update the weights becomes significantly small, effectively preventing the weights from changing at all. We call this problem the vanishing gradient problem. This essentially stops neural networks from learning any more information during training, which is obviously a huge deal for us. On the right, we see a recurrent neural network, abbreviated RNN. RNNs are networks that have a very similar structure to our multi-layer perceptron, except the connections between the units are time delayed, resulting in a hidden state which allows for better modeling of sequential data, such as language. The proposed model in this paper uses RNNs augmented with something known as long short-term memory units. Now, these units are adding gates to the RNN that allow it to learn how much to update the hidden state. Therefore, these LSTM units are helping to mitigate the vanishing gradient issue that we commonly encountered with neural networks that we spoke about earlier, because they're giving us a roadmap on how to update the weights. Now, we won't go any further into these models as this presentation isn't focused on teaching machine learning. The important takeaways here are that our model won't get stuck while training, and it has memory that will allow the context of the speech to be captured. Now let's discuss the data used. This work used a corpus of Twitter responses to produce unique candidate responses from 4 different models. 1, a term frequency inverse document frequency, abbreviated TF-IDF, retrieval-based model. 2, a dual encoder, abbreviated DE. 3, a hierarchical recurrent encoder-decoder, abbreviated HRED. And 4, a human. These responses, on top of the reference response from the corpus itself, therefore making up the 5 responses you see on the screen, were given to Amazon Mechanical Turk workers to provide a human score. For those of you who don't know, Amazon Mechanical Turk is a crowdsourcing marketplace that makes it easier for individuals and businesses to outsource their projects or jobs, such as annotating corpora. The Twitter corpus was used as opposed to other corpora because many of the models that we used above were already pre-trained and readily available on this corpus. On top of the fact that this corpus covers a broad set of topics that doesn't require domain-specific knowledge, meaning that any Mechanical Turk worker could easily annotate the score without having to know any specific information. A breakdown of the corpus can be seen in the bottom right-hand corner of the screen. While there is a bit of information here, we want to take particular note on the large number of context in the data. Now that we've discussed the motivation for an automatic dialogue evaluation model and the formation of a dataset needed to train such a model, it's time to look at the proposed model, ADAM. The researchers' goals were to construct a dialogue evaluation model that captures semantic similarity while using both context and the reference response to calculate an evaluation score. So ADAM takes in the dialogue context, the reference response, and the model response, and codes each into a vector using an RNN encoder, then computes the evaluation score using a dot product between these 3 vectors in a linearly transformed space. The formula of this score evaluation is shown at the top right in red over here. Or sorry, not in red, in black. This calculation has 2 learned parameters, or 2 learned matrices, M and N. M represents a linear projection that maps the model response into the context space, whereas N represents a linear projection that maps the model response into the reference response space. These matrices are found by training the model to minimize the squared error between the model predictions and the human score, along with an L2 regularization term. This equation is going to be shown at the bottom of the screen in blue. So we see that we have the squared error between the score predicted and the human score, and then we've got our L2 regularization term added onto this. Now, the hierarchical RNN encoder that's used has two layers of RNNs, an utterance level encoder and a context level encoder. I've gone ahead and annotated the model schematic to help you clearly identify where each encoder is. The lower utterance level encoder takes words as input and outputs a vector at the end of each utterance. The upper context level encoder takes the utterance representation and outputs a vector representation of the context. This structure is used to incorporate early utterances into the context, as multiple utterances can be fed in at once. Note in this figure that we have two utterances shown. One of them refers to this segment over here, and then another utterance over here. Of course, the diagram only shows two, but there could be many different utterances being sent through the system. Now, in order to obtain a model that can make predictions from a small amount of labeled samples, semi-supervised learning was used to pre-train the model and learn some parameters. The output of the encoder from the previous slide, that encoder has been shown here in the red box. The output from that encoder is sent into a third decoder RNN, which is trained to predict the next utterance of a dialogue given the context. So we take the context of the problem as well as the output from the previous RNN encoder, and we're going to try and predict what the output would be from a normal system. This model is referred to as the latent variable hierarchical recurrent encoder decoder, abbreviated VHRED. And this model is an extension of a previous model proposed in past literature. Now, again, we won't go too much further into this pre-training model, but it's important to understand that this model is essentially encoding dialogue context into the model early, so that Adam can learn its parameters more efficiently through its training process.
Now that we have an idea on the technical aspects, let's take a look at the experimental procedure. We start off with byte-pair encoding, which is a simple data compression technique which splits each word into subwords or characters. This is done to reduce the effective vocabulary size. A layer normalization is used for a hierarchical encoder instead of a recurrent batch normalization, as it is observed to perform better. The VHRED model is trained using the same techniques that were used in the earlier researches. The words are dropped into the decoder at a constant rate of 25%, such that the Kullback-Leibler divergence, that is the KL divergence, linearly changes from 0 to 1 in like 60,000 batches. 0 meaning they are almost identical. For the Adam model training, we use a subsampling procedure. So here what we do is, we take the model responses and place them in bins on their length and score. Then we oversample across these bins. So we pick samples from bins with the same score. So this way we get varied length responses having the same score, and the model does not use response length to predict the actual score. Because humans usually score shorter responses with high scores. So far we've discussed the training of the VHRD. Moving on to Adam. So in case of training the VHRED, we used a context embedding size of 2000. But Adam was observed to perform better when the dimensionality was reduced. And they experimentally found that the sweet spot was 50. Hence, they used principal component analysis, also known as PCA, to reduce the context, model response, and reference response embeddings to 50. PCA is a technique we use to reduce the number of features without losing the influence of the reduced dimensions. The data set is usually split into training set, test set, and validation set. Here they ensure that there is no context overlap between these sets, meaning that the model does not have any idea on the context in the test sets. That is, it's unseen during the model's training. Results. Let's see the results of utterance level correlation. New utterance level correlations were calculated for existing overlap metrics like Blue2, Rouge, etc. This was done on the full dataset. Utterance level correlation for Adam was done on the validation in the test set. It was noticed that the correlations for the existing word overlap metrics are even lower than that it was estimated in the previous studies. Adam had better correlation with human scores than the other word overlap baselines, as you can notice in these scatter plots. They also tried Adam with tweet-to-vec embedding. So instead of pre-training using VHRED, they used tweet-to-vec to fine-tune the MNN values. When this was done on our dataset, it produced reasonable results. It was still inferior when compared to VHRED, but reasonable. System level correlations. On the whole, it was observed that Adam performed far more efficiently than other baseline metrics. So, in the scatter plots, each point here denotes the average scores for the responses from the four dialogue models, that is, TF-IDF, DE, HRED, and human. We see that the humans gave low scores to TF-IDF and DE responses, higher scores to HRED, and the highest scores to other human responses. We can see that the existing baseline models were nowhere near the human scores. Adam, on the other hand, was able to give out scores that were very close to the humans. Notice that Adam achieved 0.95 Pearson correlation with human scores. Generalization ability. So, in real world use, Adam would need to evaluate the responses from models it has never seen before. So, it is necessary to test if Adam can generalize to new and unseen models' responses. To measure this generalization ability, they picked out 3 out of 4 model responses, that is the TF-IDF, dual encoder, HRED, and humans. So they picked 3 out of these at a time to train Adam and then tested the model on the unseen fourth model's response. Adam was able to generalize well for all models except the dual encoder as seen below. To relate even better, they trained Adam model on 25% less data, that is 75% of the full data set, which was selected at random. Because in the above case of 3 out of 4 models, right, we are only training with 75% of the full data. So those results were also comparable with that of the leave one out evaluation. Qualitative analysis. To understand the strengths and weakness of Adam, let's look at a comparison of human scores and Adam scores to the responses. Here in the table, we see the context and reference response along with the model response. Here, Adam scores pretty much on the same level as that of the human scores, especially when the responses are scored low. Adam does a great job there. There are a few exceptions, like for instance, take a look at the second context here. Just beat Call of Duty, want a cookie? Yes, come get it. So, in this context, for the response, I am in Kenmore at the moment. The fourth model response, I'm going to the mall, actually looks relevant, and that's why Adam has scored it slightly higher, like it is given a 2.8. But the humans have scored it a 1. Just don't know why they did it. Uh, we similarly we can see for high score responses, we notice Adam scores high for the responses. Humans have also scored high. Like we see in context 1 and 2, we can see that. But if you also notice, Adam, that it tends to be very conservative when predicting the response scores. So here, if you see in the third context, Adam assigns a low score to most of the responses, even though human evaluators have scored it high. This could be because of the squared error loss during training. So whenever the model predicted high scores, it was wrong, and it was wrong. It would receive large penalty for incorrectly predicting. So it learns to predict scores closer to the average human score and would not venture out giving higher scores than that. So this would be a disadvantage if the model is too conservative in the whole scoring. Several models similar to Adam have been proposed by other researchers that they have discussed in this paper. Like novel methods for evaluation of machine translations have been proposed. They're also pretty similar to Adam, except for the fact that in our case we need to condition the model based on the context of the conversation. But this is not necessary for machine translation evaluation. Another research has been on evaluating the quality of chat-oriented dialogue systems. Here they propose a semi-automatic evaluation metric for dialogue coherence, similar to Blue and Rouge, based on a Wizard of Oz type data. Another framework has been proposed to predict the utterance level problematic situations in a data set of Chinese dialogues using intent and sentiment factors. Then there is a model that trains a classifier to distinguish user utterances from system generated utterances using various dialogue features. There has also been a good progress in the evaluation methods for task oriented dialogue systems, which attempt to solve a user's task like finding a restaurant, booking a flight, etc. These models include frameworks like Paradise in Memo, which has a considers a task completion signal. Although these models perform relatively well, um, task completion, task complexity are two measurements that we currently don't have in our setting. References to these proposals and researchers are mentioned in the paper in case you are interested in learning more on these topics. For future work, they've also mentioned a few key areas that can be focused and could probably be improved. So, we have used a Twitter corpus to train Adam. This model can be extended to other similar data sets like Reddit. So, domain transferability of the model would be a good scope for future research. Like we discussed earlier, we see human score generic responses with higher score due to its appropriateness. So, if a model is trained to predict based on these scores, that might also score the generic responses high. So, despite having high scores, the end goal may not be achieved through these generic responses. This could be a scope for future work to remove such bias and score less on generic responses. So we can do this by censoring the length information, as we saw earlier, that generic responses are generally short, um, or by using an adversarial evaluation model. So this is a model that can easily distinguish human responses from dialogue model responses. And the model would score low for generic responses that are generated by the dialogue model. Another possible extension would be to evaluate the capability of the entire dialogue system. So instead of evaluating a single response, this evaluation would focus the end goal of the chatbots. However, it is challenging to achieve a fully automated evaluation like this. So overall, this was an really interesting paper to read and feel is a promising direction for dialogue system evaluation. Thank you.